So good evening everyone. So let's start today's session. So if you have any confusion or question, just unmute yourself and ask, please. Any questions from the previous assignment or previous classes, let's say, or in the coming assignment file?
Hello.
Yes. Hmm.
I have a question actually. Hello, am I audible?
Yes, you are audible.
So here actually in the last class, uh, when actually this Hamiltonian was taken equals to this VF sigma dot P actually,
Right.
like while calculating these Landau levels.
Mm-hmm.
So
So we are
can you please
talking about so we
for
are talk
graphene?
right. Uh-huh.
So can you please explain like how it is coming actually this Hamiltonian?
Yeah, sure. Hmm. So any other question from anyone else?
I mean, don't have a question, but just about something for the platform.
Hmm.
Like when we submit the assignments, I think so we haven't got some sort of a correction on it. So I'm not sure how we're gonna get it because we don't. I'm not sure at least that the answers I submitted are completely correct or not. So is it something which I don't know the NPTEL deals with, or is it something which you can also suggest something about?
So the assignments and everything that you do in the portal, that is actually
Yes.
handled by NPTEL and the instructor. So there is no way
Okay.
we can access as a TA. We can access your assignment and other things.
Okay. Okay.
So our
I see.
job
Okay.
starts
Thanks.
only in the tutorial session and also ends here actually.
Okay.
I have also one question. I partially understood the concept of effective mass,
Okay.
partially, but not 100% confident. And one of my question that I have also wrote in text form
Hmm.
that these quantum Hall effect and all that things, whether any instrument available in Indian labs by which we can see it or perform experiments. So only theoretical calculation, mathematical, quantum mechanical calculations are there, graphs are there, Plato are there. But what is the instrument by which we can visualize or we can see the actual things? Or in future, if we want to link with research activities in this topic. So that is my question.
Okay. Okay. Thanks for the questions. Let me start with the last one. This in the assist theory, and then we'll move to the graphene, how the Hamiltonian comes about as H bar V F sigma dot Q and so on. So quantum Hall effect is essentially a mesoscopic transport property of low dimensional system. Low dimensional, I primarily mean two dimensional system where the electron density should be low, temperature also should be sufficiently low, and the material also should be sort of clean, but not so clean that it is perfectly clean. In a sense that it needs disorder. Disorder plays a role. The plateau you see, this kind of plateau, you must have seen, right? This plateau is in stabilizing this plateau where you're changing the magnetic field, and this is, let's say, rho xy quantum Hall. You're changing the magnetic field, but for certain magnetic field area or range, you are not getting any change in the quantum Hall. So this had a role of disorder. So there are three things that I've told. One is the simply it should be a mesoscopic transport system. Mesoscopic means low dimensional systems transport measurement system. And second is my sample should be clean enough, but not 100% clean. I mean, some role is there for the disorder. And in experiment, whenever we make a realistic device or realistic material that we produce, there is always some sort of disorder, some bit of disorder always happens to be there. So clean system, and then sufficiently low temperature, and this is very qualitative and sorry, very subjective to say that sufficiently low temperature, because in graphene we have experiment where there is a room temperature quantum Hall effect that has been seen. So this is a very subjective. I mean, in two-dimensional electron gas, you have to have very low temperature, but then depending on the system, you can have very high temperature as well. Very high means of the order of 300 Kelvin. So for mesoscopic low energy condensed matter transport system, 300 Kelvin is a really very high temperature. So sufficiently low temperature, and so on. These are the kind of main criteria. There are other criteria also, uh, but uh, so now coming to the question of can we measure quantum Hall effect in India? So now we have a really state of the art instrument in almost all the uh, good groups of I mean, good groups who does this transport measurement in the condensed matter physics. So uh, I mean, all the central university, at least as far as my knowledge goes, uh, there is a measurement system which can see the quantum Hall effect. So this mesoscopic transport measurement system, one of the state of the art instrument is called PPMS, so physical property measurement system, which is expensive, few crores, I think, but nonetheless, most of the good groups have it. And clean system, we have very uh, high techniques and very advanced techniques to make samples, which are there in India also. There are dry rooms and other things there in the standard laboratory, so we can make clean system. And then sufficiently low temperature is just all condensed matter experimentalists need for experiment. So in India, there are a lot of groups that does this, or even if they do not do, in principle they can do. The only restriction that I see, or my knowledge says, is that uh, it needs high magnetic field for observing quantum Hall effect. Now, in our country, there are not really very high magnetic field setup, but those which are there is really sufficient to see quantum Hall effect in lot of systems. Graphene, of course, there is, uh, and then two-dimensional electron gas and other 2D materials also. So, so creating very high magnetic field is quite hard, and especially confining the magnetic field is also very hard. If you so mostly we use electromagnets to create uh, magnetic field. And as you know that even if we take solenoids, right? If we take solenoids, then within the very narrow range of the solenoids, the magnetic field is uniform. If once you start going outside or outward of the solenoid, the magnetic field starts the distribution of the magnetic field starts uh, behaving non-spatial. So this is one of the challenge, but nonetheless, for graphene-like system, we do see quantum Hall effect in a lot of uh, groups actually, especially ISCTIFR and almost all IITs, some prominent CSI labs, etc.
Thank you.
Okay, so coming to the next question, how does Hamiltonian comes for graphene? Low energy Hamiltonian comes as H bar VF sigma dot Q or K, let's say. So when I say Q, it is essentially measured from the Dirac point. So K is the general momentum, crystal momentum, and then K. This K is the Dirac position of the Dirac cone in the momentum space. Okay, so this is small k and this is capital K. So this is the low energy Hamiltonian. So let's see how it can be derived. Okay, so in the last class, we elaborated in detail that how can we obtain the uh, tight binding Hamiltonian for the graphene. But let's have a quick recap, and then I'll directly write the energy eigenvalue. I'm not going to calculate the tight binding Hamiltonian again, but essentially we had honeycomb structure in graphene. So this is real space picture, real space atomic arrangements of carbon atoms. So this is one type of carbon atom, and this is another type of. Okay, so this is, let's say, A type, and this is B type, and they are alternately arranged. And then in the momentum space, so okay, so the unit cell is also a rhombus type, or sometimes we also call it triangle. Both are valid description, because as long as the unit cell contains this A type and B type atoms. Uh, so this is, so this is, let's say, A1 unit cell vector, lattice vector, and then A2. Okay, and here is somewhere there is origin. And in the reciprocal space also, the Brillouin zone, or the unit cell in the reciprocal space or the momentum space, it is also honeycomb type. So, how can we get this reciprocal space vectors and then construct the unit cell in the reciprocal? It is simply we need to find B1 and B2, and the condition is A1 dot B1 is 2 pi, and similarly A2 dot B2 is 2 pi, and A1 dot B2 is 0, and then similarly A2 dot B1 is 0. Okay, and B1 and B2 are reciprocal lattice vector. Okay, so we have something like this. This should have been symmetric structure. So this is kind of rhombus, let's say. And this is one of the key points, and this is one of the key prime points, and this is in the Brillouin zone momentum space. So this along this is kx, ky, and the center of the Brillouin zone we call it gamma point, which in our case is the 0 0, and then the midpoint between the two Dirac points k and k prime is called m points, and so on. So these are some high symmetry paths, or sorry, points. Gamma point is 0 0, m point is the middle, so m coordinate will be k coordinate plus k prime coordinate by 2, and k and k prime coordinate will have according as you choose the, let's say, value of a or a2. Okay, so if we draw the tight binding Hamiltonian, sorry, a tight binding, so let me go to the previous. So I have not drawn, I think. Yeah, so I have not drawn, but we'll have some Dirac points. So the band structure will look like in the Brillouin engine, there will be 6 points where the valence band and the conduction band will touch each other, and at other points they are moving away from each other, having a finite gaps. Let's see. So we had the Hamiltonian So I'm just assuming that a lot of things have been done and starting from directly from the tide bending Hamiltonian. Okay. So we had the tide bending Hamiltonian as minus T 0 F K F star K 0, and F K was e to the power minus I K X A plus 2 e to the power I K, sorry, Kx A by 2 and cos ky root 3a by 2. So this was Fk, which was obtained from the summation of the nearest neighbor vector. So j equal to 1, 2, 3. We had e to the power minus I k dot, delta j, where delta 1, delta 2, delta 3 were the nearest neighbor vectors for a particular atom. And from this Hamiltonian, we had the energy dispersion relation as plus minus t. T was the direct hopping parameter. So this is, let's say, A, and this is B, and this is A. So this hopping strength is given by T. So this was T between two consecutive atoms of A type and B type. So this was simply, okay, so let me write the first line. F of mod of f of k square, which is 3 plus 2 cos root 3a ky plus 4 cos root 3 kya by 2, and then cos 3a kx by 2. So this was the tide bending Hamiltonian. Okay. Now, so let me go just as so how this looks like actually. Okay, so this is the tide bending Hamiltonian, tide bending band dispersion of graphene, as which you see on the screen. And there are certain points where you see that the upper band, which are positive in energy, and the lower band, which are negative in energy, exactly touches at a single point. Okay, and at other places, the bands are basically far apart from each other. Uh, So the points where the band touches each other are the K and K prime points, and the diff you see in the valence band and the top at the conduction band, the basically the middle of this kx and ky space is the gamma point, where the band gap between the conduction band and the valence band is the maximum, and there is somewhere m point between the line joining the k and k prime, where also the dispersion is gapped, meaning there is a gap between the valence and conduction band. So when you say the low energy of the band structure or the low energy band structure of the graphene, what we mean is that we only focus on the around the K and K prime point on a very narrow range, where this almost looks like an linear energy dispersion. We'll derive what the dispersion looks like around these band touching points, and it will turn out to be very exactly linear. Okay, so we had two bands here. If at the K point, if at K, and let me write KD just to be differentiate from this small kx and ky, KD and KD prime means Dirac points. The conduction band and touches each other at epsilon equal to 0. So this means that epsilon k plus, this is conduction band, and this is epsilon k minus is valence band having negative energy, are same and 0. So epsilon k plus equal to epsilon k minus equal to 0 at kd and kd prime. Okay. So this essentially turns out that this will happen. The energy will become 0 when the fk will also be 0, right? Because then Hamilton itself totally becomes 0. So we have 0 energy, let's say. So we can find. So we need to find the zeros of fk. So our fk was this one. So so the so if fk equal to 0, then real part of fk will also be 0, and individually imaginary part of fk will also be 0, right? Because fk is a complex number and it is completely 0. So that means individually, separately, real and imaginary parts needs to be 0. So what is the real part of the fk? Real part of fk will be e to the power, so from this part we'll have cos kxa, and then plus 2 cos kxa by 2 cos ky root 3a by 2 equal to 0. And similarly, imaginary part of fk will be minus sin kxa, because this was e to the power minus I kxa, and then plus 2 sin kxa by 2 equal to 0. So let's call it equation 1 and 2. So from 1, what we can get is that cos kxa by 2 equal to negative of, sorry, this was simply cos kx, and this was cos kxa by 2 so this we can write as so we have cos kxa by 2 and then cos, so let's do it from equation 2, which is more simpler to do. This is also fine, equation 1 also fine, but equation 2 I can do it more easily. So this will be sine from the imaginary part basically. This will be simply sine minus and then minus of sine. Okay, and there is an extra 2. Okay, so this part we can do sine minus minus cancels out, and then 2 cos kxa by 2 sine kxa by 2 and then 2 sine kxa by 2 cos ky root 3a by 2. So am I audible to you? Hello? Hello?
Yes, sir.
Am I audible?
Yes.
Yes, yes.
Okay.
Yes, you are audible.
So on both sides, this part cancels out, or rather we can take common sine 2 sine kx by 2 and then cos kx by 2 minus cos ky root 3a by 2 0. So from this expression we can have let's say the first possibility is that sine kxa by 2 to be 0, and then second possibility is that this term is 0. So cos kxa by 2 equal to cos ky root 3a by 2. So this happens when there is n pi, let's say, right? Sin n pi equal to 0. So cos kxa by 2 equal to simplest possibility is 0 and pi. Let's say 0 or pi. It can be 0, pi, 2 pi, and so on. And from this, the possibility, so okay, so then we can have kx equal to, let's say, 0 and 2 pi by a and so on. Okay. And from this term, so we are simultaneously solving. So if we put this part kx equal to 0, then this term will be 1 equal to cos ky root 3a by 2. And this means that again it can be, let's say, ky root 3a by 2 needs to be 0. So this is plus 1, so 2 pi and so on, 4 pi, etc. Okay, so this will translate into ky equal to 1 can be 0, and then another is that 4 pi by root 3a and so on, 2 into 4 pi by root 3a. Okay. Actually, I should take it more generally because kx can be, so kx general solution is just the uh, n pi, where n can be 0, 1, 2, 4, 3 and so on. So if you take this kx to be n pi, then you will get automatically a plus minus here. Because if you take kx equal to 0, then cos kx is simply 1. But when you take kx equal to, n pi by a, kx equal to, let's say, n equal to 1, then kx equal to pi by a. So if you put kx equal to pi by a here, so this will be, let's say, cos pi by a and a by 2. So this will be messing up a bit. So this should have been general solution would be kx equal to 2n pi by a. N is integer. Okay, that's where this sine kx by 2 will be 0. Now, if we put 2 pi by a, then this will be cos pi, right, for n equal to 1. So this will automatically include plus 1 as well as minus 1. So in general, this is plus minus 1. So from this we can have all the possibilities, and this can be negative as well as positive. Okay. So one possibility, let's say, is that kx equal to 0 and ky equal to plus minus 4 pi by root 3a. Yes, that is one possibility. And similarly, we can find other possibilities. So in total, we need to get 6 Dirac points, okay, corresponding to the 6 band touching points that we have seen. So this already gives me two Dirac points. One is this 0 and 4 pi by root 3a, and another one is 0 minus 4 pi by root 3a, let's say. So this means that here one of the Dirac point lies on the y axis, right? So we had something like this Brillouin zone kx and ky. So this is my, let's say, plus 4 pi by root 3a, and this is minus 4 pi by root 3, whereas x remains at 0, kx coordinate remains 0. And then we can have other corner Dirac points. So this is, let's say, k Dirac, and this is, let's say, k Dirac prime. And similarly, we'll have another Dirac point here, and they come in a consecutive manner, I mean alternate consecutive. So if there is kd in this point at the top, then the next will be kd prime, and then again the next will be kd, so that a alternate arrangement is there. So this we can find by solving all the possibilities. Okay, so this will be kd and this will be kd prime. Now one question comes that why, so if there are 6 Dirac points, then why only we call about, or we only talk about 2 Dirac points, right? That's because our so this is hexagonal Brillouin zone, but if we observe the rhombohedral Brillouin zone, or the Brillouin zone which looks like a rhombus, uh, so this one, then you see that only 2 Dirac points are covered, and this is actually the Brillouin zone. So this is more of an Wigner-Sage cell. Okay, so this is actually Wigner-Sage cell, and this rhombohedral part is the Brillouin zone in momentum space. Brillouin zone always refers to the momentum space unit cell, K space. Okay. So in the Brillouin zone, there are only 2 inequivalent Dirac points. All others can be made equivalent by this lattice translation vector in the momentum space. So let's say I have a general vector k, okay, in the momentum space. So k plus g is the lattice vector in momentum space. Then k plus g is simply k. It is equivalent, right? In terms of energy and other things. So this condition makes that there are only 2 inequivalent Dirac points. What do we mean by that is that kd, you cannot have some g which will be again kd prime, let's say. This cannot be true. Okay, this is not true actually. But other Dirac points, so if we, let's say, so if we focus on this Dirac point and kd for this one, let's say 1, and you will have some g. Again, g is the reciprocal lattice vector. So n1 b1, n2 b2, n1 and n2 are the integer. So it is a combination of b1 b2. So you will find that with some suitable g, you will find that kd of 2, let's say, you will get. 2. And similarly, you will also find this can also be there, kd of 3, and so on for the kd prime. But these two, you cannot connect with any form or any combination of reciprocal lattice vector. Okay, so let's go ahead with this set of Dirac points, let's say, okay, kd and kd prime, or let's call it kd, 0 and 4 pi by root 3a. Okay, so what we have found so far is that zeros of fk in the Brillouin zone, right, in K space. Now we need to have the Hamiltonian around those Dirac points, and we'll see that how the form looks like. So for that, so since the Hamiltonian is simply given by minus t0 f of k and f star of k 0, so if we just expand f of k around those Dirac points, then it will simply give me Hamiltonian around those Dirac points because of this expression.
Hello.
Yes.
Actually, can you please explain briefly, like, why we are interested in having the Hamiltonian around the Dirac points while calculating the Landau levels?
Okay, there are two
Like,
reasons for this. Uh,
okay,
okay, so let me complete this sentence and I'll conclude this.
okay, sure.
Uh, so, uh, so if you see this Hamiltonian, uh, so this is fairly complicated Hamiltonian, even in 2D, sorry, 2 by 2 Hamiltonian, right? This is a 2 by 2 Hamiltonian. This is fairly complicated because of the form of FK.
Yes,
It is quite difficult to deal with this kind of expression all over the place while doing calculation, especially analytical calculation. So, uh, so one of the objective is that since we found that the around some band touching points there are sort of, so this is even becoming quadratic, it should be exactly linear. So as we found that around the band touching point these are almost like linear. So if I confine my experiment, or if I confine my physics, if the physics is confined around the low energy, so remember that this was the zero energy, and as we go up it was increasing energy, and as we go down it was the increasing energy in the negative direction, right? So, and in the mesoscopic transport most of the transport happens around the around the low energy. Okay, so that's why we sometimes call it in condensed matter physics the low energy states uh, only matters and it only contributes. So what do you mean by low energy? Again, it's a subjective thing. Low energy means that this is the Fermi energy. Okay, this is the pristine Fermi energy. Pristine means you have not applied any electric field and so on, and you have some Dirac materials. I mean graphene, uh, and there is some Fermi energy in the system, right? For the fermions. So you'll find that the Fermi energy exactly lies at the uh, top of the valence band. So what this necessarily means is that up to this point, or the valence band is completely filled, okay, and the conduction band is completely empty. So this is the equilibrium situation, and those energy spectrum that we draw, actually it's kind of like that, energy minus Fermi energy. That's why you get exactly at the zero energy. I mean band touching at the zero energy. Now again, I'm deviating a little bit, but let me explain. I think this will make things more clear. I hope so. So if of epsilon, and this is let's say epsilon or mu, whatever you take, better take epsilon, and this, let's say I'm drawing Fermi energy distribution at the exactly zero energy. So this is, let's say, zero energy, P equal to 0, and this is mu, right? And along this energy is increasing. So okay, so I'm not calling mu, epsilon F Fermi energy. Now this is the equilibrium situation for any fermionic system, irrespective of graphene or 2D electron system and so on. This is just the Fermi energy versus the energy at zero temperature. Now, when you give any perturbation to the system, perturbation means, let's say, electric field. If you want to measure transport, then you have to give electric field. Only magnetic field is not going to give you any transport. Okay, magnetic field will just create Landau levels and so on. But for transport, electron moving, you need electric field. So when you give external perturbation, the state which are near the Fermi energy is going, the probability that these electrons which are near the Fermi energy is going to get excited and going to get in a new state which was previously empty and conduct electricity and so on, right? With the electrons which are deep down the Fermi sea, let's say around this energy, they have a very high energy barrier. This much energy, if epsilon F is needed in order to have conduction or in order to get there from any other empty state. But around the Fermi energy, there is a strip, let's say. Uh, these electrons are very susceptible to conduct because they need very small amount of excitation and they will start moving and conduct electricity and so on. So this means that around the Fermi energy in condensed matter physics, around the Fermi energy, the electrons which are around the Fermi energy are the most interesting in the context of transport. Okay, and the band structure that we draw is that energy minus epsilon f and how it goes over k and so on. So when you say that we have graphene band structure have something like this, and this was epsilon minus epsilon f, and this was k. So essentially, my most of the electrons which will conduct electricity or which will participate in the mesoscopic transport is those around the Fermi energy, and the Fermi energy was 0 for a pristine graphene system. And around this Fermi energy, we have a linear dispersion. Okay, that we can calculate. We will calculate. So what was your precise question? So this was kind of context.
Yeah, actually I got my answer actually. Thank you. These things. So I wanted to understand like why for calculating the Landau levels we are only interested in that linear dispersion region instead of that whole Hamiltonian. So I understood these
Uh,
things.
so
Thank you.
that's one part of
Yeah.
the answer, that we are interested in the low energy regime, and I explained that by low energy, what do we mean? The states which are around the
Yeah.
Fermi energy. That's one reason. Okay,
Okay.
and the second
Okay.
is that we cannot analytically solve tight binding Hamiltonians even for the simplest 2 by 2 cases of graphene.
Okay.
Probably there was one or two lecture in the Hofstadter butterfly. You see, when we give magnetic field in the tight binding Hamiltonian, how complicated the situation becomes. There is no way you can calculate, almost analytically at least. It is very difficult.
Okay.
The only way is to numerically. So, but then numerically is a very it's a kind of black box, right? You give
Yeah.
right code things and result comes out, and you have to explain things, which is good and which we routinely do. But if we have analytical calculation which is relevant for the system as well, then you will have lot more understanding and lot more insights into the problem. So this is one of the problem. This is one of the, we are fortunate that first of all it is low energy, so we are having linear dispersion, so it is a very easy to calculate, and this is giving me also the experiments that we are doing around this low energy. So this, there are twofold reason primarily.
Okay. Okay. Thanks.
So now let's get back to the formulating Hamiltonian and the low energy. Okay, Okay, so we need to expand Fk around the Dirac points, which will give me Hamiltonian around the Dirac points. So Fk will simply expand just by using Taylor expansion. So del F Taylor expansion, and we will also apply the partial. So this is one of the Dirac point, let's say, and then Kx minus Kx. So Kx d means Dirac point coordinates, and then for there is f is function of also qi, so we'll have del f del qi, and at kd I'm not using vector, but all of those are vectors. These are vectors, let's say qi minus qid. So this is again Dirac point coordinate, and so on. This will have del 2f del kx2 kd kx minus kxd square plus del 2f del ky2 kd ky minus, okay, so there should be half, I think, kyd square by 2, and so on. But we are interested in the first two terms, because we so if the first two terms are non-zero, then we will stop at there, and then if there is no kx linear kx and ky term, then we will go to the higher order term. But it turns out that these are non-zero, so we will not go to the higher order second order derivative term. Okay, so if we calculate del f del kx, this will be, so we had, so minus ia e to the power minus I kxa, and then ia by 2, so it will give me plus ia e to the power I kxa by 2, and then cos root 3 kya by 2. Similarly, del f del ky will be, this part will be 0, and this will be 2 e to the power I kxa by 2, and root 3a by 2. So derivative of cos negative sine root 3 ky a by 2. Okay, and this we need to find out at kxd, which is 0 in our case. If we take, let's say, kd, Dirac point is 0, 4 pi by root 3a. So let's say we are working with this Dirac point, then this kxd will be 0, and this we need to find out at kyd will be simply 4 pi by root 3a. Okay, and so I'm not explicitly solving this, but okay, so if we need to solve, then what will happen? Del f del kx will be minus ia, this will just be 1, and plus ia, again 1, cos root 3 kya by 2 del. So this is at kxd del f del kyd minus 2. Okay, so this is actually not correct. When I say this, we only need to evaluate at kxd equal to 0. Okay, this we actually need. So as I wrote here, kd, this is a vector, so kd, this is also kd, so we need to put both kx and ky values. So ky here, ky will be simply 4 pi by root 3a. Similarly here 2 into 1 into root 3a by 2 sine root 3 root 3a by 2 into 4 pi by root 3a. Okay, so this part will be simply minus ia. Right, so this is minus ia, and then so we have cos 2 pi, which is again 1, so plus, what is that, plus ia equal to 0, and then we'll have sine root 3. So this is again coming 0. This would not happen actually. So it will be del f del kx. So what coordinates 4 pi by root 3. This is also okay. And there is some mistake that happened, I think. Otherwise, this if del f del kx should not have been uh, 0 actually. It should have some value so that this where root 3 should be there. Oh no, sorry, not here. It's okay. So what I need from this, just by looking at what I get the Hamiltonian in terms of k, is that del f del kx should be some constant value. So this should be some constant value, and this should also be some constant value, so that this kx and this ky term survives, and essentially we have this kind of Hamiltonian where this will be h bar vf. Vf is in terms of will be t, some function of t proportional to t, and then we'll have some let's say qx or uh, yes qx, where qx I'm writing as kx minus kxd, and then minus I qy and qx plus I qy 0. So this should be my form. So effectively f of k should reduce to qx minus I qy, and this should come from this term only. So this you can write as qx and this as qy. So del f del kx should give me qx simply, and del f del qy should give me minus I qy. or simply minus I, because Qi was already there. So 1 and minus I. This should have been my result. Okay, so I'll do from the scratch. Somewhere in between, I think there is a mess up, and I can send you the solution over your email actually.
Okay.
So you can just write the email ID. I'll just note
Okay.
it down.
Okay, sir.
In fact, all of you can write down the email ID. So I'll send an email. But at least the procedure is clear, right? There is no problem in the procedure. Okay, there is some
Yeah.
mess up in the calculation itself.
Yeah. Yeah. Okay. Okay. Thank you. Uh, have you got the email ID?
Yes, yes.
Okay.
What is the I one word which is very often used, hopping?
Mhm.
So, what is exact meaning that actual? I'm not clear about the correct meaning of hopping. It is Basu sir has many times used this word, and you are also in a small T case.
Right. So, okay. So wait till. So this was actually we explained a bit, I think, in the previous class. So there are two, three ways we have. Sorry, I just need to charge it. So if I explain in a very qualitative way or very vague way, so in metals, in conventional metals, let's say, we just take the electrons as if they are free and they have no kind of bound. I mean, they have some bounding energy. That's what you read in photoelectric effect and so on. But they are essentially quite free. Once you give or apply electric field, they are free to roam. So, due to the acceleration faces by the electrons due to electric field, they start conducting. Right. So that's the simplest picture. And that's what we call free electron and parabolic bands and so on. Right. H bar square k square by 2m. So this is a very preliminary and very idealized situation of the Drude model of conductivity or Drude model of transports. That's what you read in the first chapter of any conventional condensed matter book, let's say. And after that, so there are many drawback of this free electron model, but one of the drawback in this context is that this free electron model, that electrons are essentially free, doesn't account the fact that there are ions sitting in a arranged manner, in a periodic manner in atoms, or sorry, in a solid state system, and those ions have electrostatic potential, right? Nucleus is a positively charged and electrons are a negatively charged, so there will be some potential due to the positive and negative charge, right? So those potentials are periodically arranged in a solid state system. And this fact has not been taken into account in the free electron theory. So the first step to correct this thing is that free electron, but very free electron in a very weak periodic potential. So there are three steps I explained in the last class, I think. Uh, yeah. So this one. So there are three models, let's say. One is free electron model that I explained. One is weak periodic potential, which is again, this one is the weak periodic potential. Let's say essentially we'll still assume that the electrons have free electronic dispersion, almost free electronic, but the only thing that will add there is a periodic potential, V0, let's say. Okay. This potential is coming due to the periodic arrangement of ions. and there is potential associated with the each ion due to the nucleus, core, and so on. So once we incorporate this V0 periodic potential, and we assume that V0 is quite small compared to the free electron energy, which is given by this h bar square k square by 2m, then we get, so this was my free electronic parabola, right? Continuously going on as k increases. So this is the direction of k. Once you take into account of the periodic potential, you have the formation of energy bands, let's say. So the formation of energy band. So you will not get the continuous energy spectrum like this, but you will have some energy spectrum like, so let me draw here. So you had some continuous energy spectrum of free electron energy, and then once you take into account of that V0 plus h bar square k square by 2m in the Hamiltonian, then you will get some energy band. So you will have some energy states like this. So this is energy and this is k, and then there will be a gap, okay, and again you will have some like something like this. There is a gap, and then again you will have some bands like this. So from continuous energy spectrum in the free electron model, you get a discontinuous energy spectrum where up to this point there is a band, and if you start from this energy, which is let's say 0, you can at max go to this energy, okay, and in between, in this range, in this small range, let's say this is red colored small range, you cannot have any electron because there are no states, there are no energy states there, okay. And again, once again you can start from this part. So again you can start from this part, and you can have energies, okay. So these are called bandwidth. So this is the maximum of a band, and this is the minimum of a band. So this is the bandwidth PW, let's say, and so on. This goes on actually, okay. There are a lot of bands depending on the systems. So this was the second process. Electrons are still free, but there is a very weak effect of the periodic potential. However weak that periodic potential may be, once you incorporate this V0, you will have separate bands, okay. So this was the second thing for a electronic band structure. And so essentially we are making the problem harder and harder. You started with this simple free electron model, there is nothing, it's just free, and then you say no, there are ionic potential you need to incorporate, but then ionic potential are very less, let's say in magnitude or strength. So you do perturbation theory, and you get this kind of discontinuous spectrum formation of bands, which is in the formal language. And then essentially V0 may not be small actually. So this was our crude approximation that V0 is small, but in an ionic system, or sorry, a solid state system, it need not be small. So the next improvement on the band structure or the electronic bands theory is that we consider atoms. So there is some drawing, yeah. So these are, let's say, these blue dots, let's say, are the ionic positions in the periodic. So I am drawing in 1D, but this can be easily extended to 2D and 3D and so on. So this is, let's say, first ion, and this is, let's say, second ion, and this is third ion, and so on. Okay. So in the tight binding system, what we call, or what we assume, is that the electrons are tightly bound to their own ionic core, okay. So I have some atoms. So even if we talk about carbon atom, let's say we'll have carbon 6, right? So we'll have 1s and then 2s and then 2p. So 1s2, 2s2, 2p, this will be 2, I think, carbon 6, yes. So so we assume that so this is, let's say, nucleus of the carbon atom. So the electrons of the outermost shell, which participates in the electronic transport and so on, are tightly bound to their electronic core, ionic core, or the nucleus core. Here this is not ionic, simply uh, nucleus, and so on. So this continues for the all the carbon atoms periodically arranged. Now what we say is that there is a development of the potential, right? So this is ionic potential, which is in the negative, because positive and plus nuclear charge, let's say Qn nuclear charge, and this electrolytic charge. So this will be negative. So the potential is negative. So this effectively you can treat, or very in a very crude way, you can think that these are effectively potential barrier problem. So you have some, so these are, let's say, atomic orbitals. Let me draw different colors maybe. Okay, so these are, let's say, atomic orbitals concentrated around these particular atom. So if I am talking about, let's say, third atom, uh, on electron, on 2p electron of the third atom, then it will just be, sorry, then it will just be concentrated around the third atom, right? Again, similarly, if I talk about the any electron which are of the second atom, then it will be concentrated around the second atom, right, of the carbon. So these atomic orbitals are concentrated around the nucleus, but nonetheless there can be small overlap in this region, okay, in the atomic orbitals, and each electron faces this much of periodic potential. I hope you can see it. So this much of periodic potential, and this is kind of potential barrier, so that electrons are essentially cannot roam freely. And then we say that in tight binding model, we say that although electrons are tightly bound to the each of their own atom, first, second, and third, but there can be some probability that electrons can hop from this first atom to the second atom. So first, one of the electrons which are of the first atom, it can actually go to the second atom, and so on. Second atom can go to the third atom, and in fact, quantum mechanically or probabilistically, first atom's electron can hop to the third or fourth, and even any case. Okay, the point is key, if the electrons are tightly bound and very concentrated near its own atomic core, then then the probability of hopping that electron from the first atom to the, let's say, fourth atom is going to decrease, and so on, right? So the hopping probability, that means that electron can hop from the first to the second. So there is a finite tunneling probability. If you have read this tunneling barrier problem I have in quantum mechanics, so let's say this is V0, and one electron or quantum mechanical particle is coming with an energy E which is less than V0. In classical systems or in classical physics, there is no way it can barrier or it can cross the barrier of this type, right, where energy is less than the V0 potential energy. But in quantum mechanically, there is a finite probability of tunneling through this barrier, even if the energy of the particle is less than the potential barrier. So this is what it means by hopping, that even if the energy of the electron is less than the potential barrier, it has a finite quantum mechanical probability that it can hop or it can cross that barrier of this one atom to the next atom and next nearest atom, depending on the system. So this, in a simple language, we call hopping. So electron are as if hopped from uh, each of their own atom, let's say. I hope this was clear. It was very vague, but all of these have a very beautiful mathematical construction.
Yes, thank you. But I think one more thing, that is what I have read in Croning-Penny model. I seems that is quite more similar concept that
Exactly.
you have explained.
Kronig-Penney model was a kind of introduction to this kind of thing, actually. Okay.
Okay, thank you, thank you.
Okay, so I'll send these notes, detailed derivation, but this was the procedure
Uh,
and
I have
uh, so.
uh, I just have two quick questions.
Mhm.
So in context of the lectures notes, there was a section about effective mass of Dirac fermions, like in graphene.
Mhm.
So Professor Basu talks about the anomaly that he redefined like the definition of effective mass because it's needed because if we take the traditional definition,
Mhm.
it was giving mass to be like infinite, because our dispersion is linear. So if we take the double derivative, is infinite, but we are telling them to be massless. So he redefined it. So why this? How this redefinition come from? I was a bit confused. Like, okay, I understood that it's needed, but I don't see the motivation of why that particular definition, or how it suggests the idea of redefinition.
Okay. Mhm.
Uh, so that's the first question, and the second question was essentially about that when we derive this expression. I mean, again, the dispersion relation of Landau level for graphene.
Right.
Uh, the lowest Landau level at n equals to zero was like, in the lectures, the Professor Basu said that it was spatial because it receives contribution only from one sublattice.
Mhm.
So I was not sure like how from only one sublattices, like either from A sublattice from Dirac point K, or from B sublattice of like Dirac point K prime.
Right.
And all other Landau level receive some contribution from both of them, but the lowest one receives only from one of them. So I could not able to see how one can infer that. So if you can comment on both of them.
Mhm. Okay. I think both the questions are interesting. So thank you for that. But let me answer
Mm,
the first question, and the
sure.
second question is quite difficult. I mean, quite involved.
Okay.
And in
Okay.
fact,
I see.
sort of tend to start from that actually in today's lecture.
Ah,
I
okay.
determined to start from the from deriving Landau levels for low energy graphene, which is linear in K, from an
Yes.
operator perspective. Because I think that operator perspective gives you very clear picture that that the zeroth Landau level is something special at K point if it is concentrated around the P sublattice, then at K prime point it will be the other way around. And that you can actually clearly see from the construction of the Hamiltonian, and what we need in terms of wave function or spinor function, let's say. But
Mhm.
nonetheless, let's try. Okay, so
So if you can suggest some, I don't know, resources, so I can, I mean, check by myself, and if I still find myself a
so
problem, I can.
I think we'll have some time. So it is already only
Ah,
seven,
sure.
so
Okay.
we'll have some time.
Okay. Okay. Sure.
Okay, so conventional effective mass is given by simply h bar square del 2 epsilon k, or yeah, del k2. So this is just the inverse of it.
Yes.
Now epsilon k of graphene around the Dirac points is simply given by h bar vfk. Let's say this is plus minus, and here k is kx square plus ky square. So del epsilon k of del k will simply be plus minus h bar vf. Now if I take double derivative, del 2 epsilon k del k2 will simply be 0, right? Because this is
Yes,
independent
sir.
of k.
Yes.
So
Yes, sir.
that
Yes.
means m star becomes h bar square by this term. It is inverse. So by 0. So it tends to infinity. On the other hand, we are saying that so this type of Dirac cone, it is massless Dirac cones. So this is the anomaly that one faces while using the conventional derivation of, or the conventional expression of effective mass when we apply that in for
Yes,
the
sir.
Dirac particle. Now, so this we call massless. Now, the way we approach this problem is simply the effective mass is kind of the mass that an electron experiences or the electrons kind of have in the solid state system, and it is different from the electronic mass. So m star is not equal to m, obviously, and moreover m star is dependent on k, right? uh, the key points in the Brillouin engine, let's say. And one of the very vague way to think about that is that if I have a simply parabolic dispersion of this, then the electronic velocity, so so the velocity at this point and velocity at this point and velocity at this point are different, right? So these are, let's say, A, B, C points, and this VA not equal to VB not equal to VC. So at each point the velocities are different. So if we apply electric field, then the acceleration that electron will experience, we can think of that it will also be different, right? Because the velocity itself, so velocity means simply del f, del epsilon del k, and there is 1 by h bar. So from this, we just roughly understand that, okay, in the solid state system, an electron or the conducting electron, uh, it's kind of having effective mass is different. So all of these periodic effect, I mean, sorry, the lattice effect, that, and if you have a free electron in a free space, there is no ionic potential and so on. It just be simply be given by me, and then velocity, and then d dt, right? The force. But in a solid state system, this velocity itself, so have I done something wrong? No, it's okay, right? dp dt.
Yes.
But in a solid
Yes, sir.
state system, this V itself is different at different k points. It depends on the where, at what energy you are in, or at what k point corresponding to at what k point you are in. So essentially, this acceleration or the force will be different. So this kind of in a crude way we understand by saying that the electronic mass of an electron in a solid state system is dependent on k, and it is not the same as the electronic mass. So that's the main, I mean, very crude understanding about the effective mass. So, so from this understanding, we essentially say that the momentum is given by simply h bar k, number one, crystal momentum, and then this is also should be related to the Vg, m star Vg. M star is the effective mass, and Vg is the group velocity. So it's kind of average velocity with which an electron moves in that system. Okay, so from this we derive that P equal to h bar k, h bar k, and then this is m star. Vg is simply given by 1 by h bar del epsilon del k. And if we use this expression, then we'll have m star equal to h bar square k, and then so del epsilon del k inverse, right? So if we use this expression, then we'll have del epsilon del k for graphene is simply h bar vf, nothing, the k is gone, so this will be h bar square k, and then h bar vf. Okay, so inverse, so that means h bar k by vf. So this is the effective mass for graphene around Dirac points. Okay, yes, this is h bar vf, sorry, h bar k by vf, yes. And this effective mass at k tend to 0, this becomes m star tends to 0, right? Because m star is simply proportional to k.
Yes, sir.
So from this we bring consistency that the conventional expression cannot be used, and as k tends to 0, which is the Dirac cone, so this is the Dirac cones, and so this is k, let's say. So this is the center, let's say, and at k equal to 0, at this exact nodal point, the electrons are massless. As you move away from k or increase the k, then similarly you will also increase the energy, and similarly you will experience some mass. So that's how we bring consistency that around at the k tending to 0 limit, the electrons should be massless for the graphene, and that's how we can get from this expression. Okay. Now, what was your precise question?
In Croning-Penny model, he says that behavior of electron is also changes. Sometime it behaves like a positive in some region of conduction band because mass is increases and mass is increases. That shows positiveness because positive are more heavier than electrons. So that type of concept is also available here or something else.
No, so I think you are talking about electronic mass and whole mass, right? That's one of the way that you said in terms of understanding that electronic mass and whole mass. I mean electronics charge and whole charge, and electronic conduction and whole conduction, and so on. But here we a similar concept is actually applicable here also. Here we just say that the conduction band carriers are the electrons and valence band carriers are the holes, basically.
Okay. One more thing, one also has question in assignment that area of primitive cell, unit
Hmm.
primitive cell.
Hmm. Right.
So area means surface area or inside the area of cell.
No, no. Area of primitive cells simply just means that what is the area of that unit cell. So
Yeah,
you have this kind of A1 and A2, right,
yeah,
in the graphene, and A1 will have some expression. I'm not going that. A is the difference between the two carbon atoms, and so on. So how do you get area? So this area is simply given by again a rhombus type A1 cross A2. So this will be the area. Mod of this will be the area of unit cell. You
so
see.
we have to mention any numeric value also that somewhere in some literature they are also given numeric values of this area
I
that
think,
0.052 nm square that type.
yeah, I think this expression, and then you take A to be 2.446 angstrom, right?
Yeah.
Carbon-carbon distance in graphene. So whatever value will come, it's just fine. So you write both of these, root 3 by 2 A square, the formula, and then exact numerical value.
And one thing also, sir, I am first time entering in this NPTEL course,
Mhm.
and the method is pen paper method. So the derivation is very long, very explicit. So in final question paper, we have to write all details derivation that explained by sir and you, whole
Uh,
derivation.
No, so in any derivation, there should be sufficient details, but not all the details. Meaning, if a few things are kind of common and kind of it is absolutely necessary, so you need not go back all the primitive things. But I mean, there should be, you can jump some steps, not all the steps. That's my point.
Okay, thank you.
So try to make it as self-explanatory as possible. But again, sometimes it is not possible for everything to write in
Yeah.
a time. Okay, so there is one more way to understanding this massless graphene system question. So the Dirac Hamiltonian happens to be P dot C, some alpha, let's say, and then some beta m0 c squared. That's what the general Dirac Hamiltonian that we talk about in high energy physics or in general uh, quantum mechanics 2 course or relativistic quantum mechanics. Given. So what we have in term for graphene is that simply h bar vf sigma dot k, right? And if we rearrange things, we can think of like vf is the velocity, so I can make it even vf and h bar k to be p. So this is p dot vf, where p is h bar k, and vf vector is simply nothing but vf sigma vector. Sigma vector is composed of three uh, Pauli matrices, sigma y, sigma x, and sigma z, and there is nothing, right? So where in the Dirac Hamiltonian, general Dirac Hamiltonian, m0 was the rest mass, and here we have m0 equal to 0 for graphene. So that's why we call it massless graphene system or massless Dirac particles, which realized in photon, right? Photon only have h bar kc, let's say, or just pc. It's better to write pc simply. That
Yes,
c
sir.
is the light velocity, whereas vf in our case is not the of the order of 10 to the power, sorry, 10 to the power 9, but it is even 10 to the power 3 order lesser. So it is actually happens to be 10 to the power 6 meter per second of the order of. So this is just to bring consistency actually. Okay, the old formulation doesn't work, which is kind of
Yes.
understandable because we are dealing with some kind of relativistic particle compared to the free electron particle, which are more of a normal quantum mechanics. So there is a clear-cut distinction between conventional quantum mechanics and relativistic quantum mechanics, right? So that's why this anomaly comes actually.
Okay, sir. Thanks a lot. So, like as you explained that this is essentially effective mass is a property of the dispersion relation,
Right,
and
right,
since the dispersion relation is like okay, it changed, so the definition got redefined in such a way that there is a consistency within the
right,
formulation of.
right.
So, but at last, like when you derive the new definition, you say this m star is h bar k.
Hmm.
Uh, mm, uh, so if k goes to 0,
Right.
then m star goes to 0. So, I mean, I understood this as a relation that it's true, but like, do you have some physical way of thinking about it, like that? Because k going to 0 means crystal momentum going to 0, but still my like electrons are within the tight binding model. So why effective mass got like 0? I try to
Okay.
understand it in terms of some physical picture if I can.
So physical picture. Okay, so I think I'll repeat what I am saying actually.
Yeah.
Uh, so let me go. So I have some pictures. So this is my graphene band structure, right?
Yes,
So
sir.
the picture is quite bad, but anyway. So this is the so this is the key point, and around this point, you see that this is kind of you can make this approximation, right?
Yes, sir.
Now, when I say so this is the complete tight binding Hamiltonian, which I was saying that gamma point, which was at the Brillouin zone. So if I again draw the Brillouin zone, this was something like this, and this was gamma point. Sorry, gamma point, and this was middle point was M, and this is one of the Dirac point KD or K. This was K prime D or simply K prime. So you start from the gamma point, which is 0, 0, center of the Brillouin zone, let's say, center of this hexagonal form of Brillouin zone. The energy are the highest, right? And the band gap is also highest. It almost goes till 9, sorry, 10, 10 and minus 10. And then as you go along this path, this highlighted path in the orange, so you start from gamma and then go to M. Some energy reduces to this level for both the conduction and valence band, and then you traverse this path M to K. So you are traveling from gamma to M and then M to K, and then again you are coming back to gamma. So as you go from M to K, so you are further reducing the energy gap between the valence and conduction band, and at exactly K point, around the K point, at a very narrow energy range. Okay, So this might be around the only maybe 0.1 EV or something like this. Okay. So when you say this linear energy dispersion, massless, all of these are actually concentrated around 0.1, 0.2 EV. Okay, so this is almost like an MeV range, right? So 10 MeV or 100
Yes, sir.
MeV, something like this.
Yes, sir.
So around only this region, which is again, which falls at the K point, you have this linear dispersion. So energy is proportional to simply K. So
Yes,
when
sir.
you say that this M star goes to zero around K goes to zero, that means this redefined or this M star expression and then the whole concept that the massless Dirac fermions and so on, all of these are
Yes, sir.
valid around this concentrated region. You cannot say these are massless. Okay, these have a finite mass, finite, very huge energy, and so on. But and this is not even linear. You cannot say these are linear. This looks like linear, but it is not linear. If you see the
Okay,
expression,
sir.
please.
Mm-hmm.
So
Yes, sir. Yes,
so
sir.
so then we say that so that's the reason that around K point we have K equal to 0. Okay, so this needs to be
Okay,
clarified
sir.
that when I say
Now I
K
see it.
equal to 0, yes, when I say K equal to
Yes,
0,
sir.
it is actually Q equal to 0 because Q was
Mm.
K minus KD, right?
Yes, yes. Okay.
So
Cool.
K equal
Yes.
to 0 means with respect to the Dirac point coordinates. So this is actually Dirac point coordinates. That's why we take K equal to K tends to 0 limit.
Okay, sir. Okay. Yeah, now I see it. Thanks. Thanks a lot.
Okay, so now let's move to your second question that so what was the question? Question was that zeroth lambda level was special and it was concentrated around some sublattice.
Yes, so there was a contribution by one sublattice, say
Right.
sublattice A or B, but for other Landau levels, there always been contributions by both of the
Both,
sublattices.
right.
So yeah. So like my question was essentially like I don't see how n equals to zero was spatial. If I could just stare at the dispersion relation of the Landau level of
Oh no,
graphene.
that you cannot tell. Okay, so
Ah,
this
okay,
dispersion
okay,
relation is just the simplest of the what is happening in the background. So you need to know
okay.
at
I
least.
see.
So I
Mhm.
can explain more mathematically. At least today I do not have much physical way of motivating that why it should be the case for the zeroth Landau level. But I will say it kind of more mathematics wise.
Okay, sir. Mhm.
Okay. So let's start from the linearized Dirac Hamiltonian, which is the linear dispersion. So we have Hamiltonian like h bar Vf k dot sigma, which I'll alternately use both actually, Vf p dot sigma also. And so the my Schrodinger equation, or let's say the Hamiltonian equation here, not Schrodinger, rather Dirac equation. This is so simply be psi, and this is given by Vf E dot sigma psi equal to E of psi. So psi have some 2 by 2 structure, right? Sorry, not 2 by 2, 2 by 1, because Hamiltonian is 2 by 2. So psi is 2
Yes,
by
sir.
1 and energy have some 2 values
Yes,
and psi will have some again 2 by 1 values.
yes, sir.
Okay. So once you give or apply magnetic field, and it will be represented by again curl of A, let's say is the vector potential, then you will have Vf, uh, just I'm reversing sigma dot just to convenience, not an issue, and then P minus Ea psi equal to E of psi. from this expression, if we write it, okay, so let me choose again the Landau gauge, and this is, let's say, given by minus by 0 and 0. So only ax not equal to 0 or others are 0. So this will be Vf sigma x and I h bar del x, let's say I'm writing px, and minus e of minus by, this is ax, and plus sigma y, simply py, or I can also write minus I, so there will be minus I and minus I h bar del so this actually be kx, no sorry, I am writing p, so this is x, this is x, this is y, del y, and then psi equal to energy and psi. Okay, so again the same story, that uh, our choice of Landau gauge is such that the electrons are free to move in the x direction, because there is no x in this expression apart from the del x. But in y direction, this is confined, or it will not have free electron like dispersion because of this gauge choice minus by. So, so again, we will take the similar function. Wave function should look like something free energy dispersion along the kx, whose wave function is given by to the power I kx. Here I dot kx actually, not the I kx. It is not the kx. Okay, and then there will be some phi y, which again have 2 by 1 structure, spinor structure along the y direction. So if we use this psi, then we'll have simply h bar vf sigma x and kx minus, sorry, plus eby plus sigma y uh, minus I h bar, and then this is del y psi e psi, right? Okay, so this should be h bar kx. Now we just write down the Hamiltonian in a matrix form, let's say. So if we write this, so this is Hamiltonian H cap, which is, let's say, Vf, and then if you write in matrix form, because sigma x and sigma y are the Pauli matrices, so it will be 0, uh, E Vy by C, sorry, not C, E Vy, and then minus Kx and minus del y. So my writings, okay, so let me write it more clearly. Things will be more clear. So one more steps. Basically, so this will be Vf. Sigma x means 0, 1, 1, 0. H bar kx plus Eby plus Vf. Sigma y means 0 minus y I 0 minus I h bar del y, right? This is my Hamiltonian. And if we just do the matrix addition, then it will turn out to be EBY plus h bar kx minus, so Vf is there, and h bar del y, and similarly here also same, just the complex conjugate minus, sorry, plus h bar kx plus h bar del y, right? So this is plus because I and I square is minus 1, and here there is a minus, and 0. So this is my Hamiltonian. Okay, now we will introduce a new variable which will be
May,
uh,
maybe I think you left VF
so
in the
Vf is
second.
there in the outside actually. Okay.
Uh, okay. It's okay taken out. Oh, sorry. Yes. Okay. Cool.
Okay, so what we'll do is that, so we need to do define a new variable which is, let's say, xi equal to y by lb minus lb kx. So I left some minus sign.
I think complex conjugate you have right. So in matrix minus h cross kx is there. I think it may be wrong.
Maybe I left one minus sign, I think. Let me see. No, I think it is correct. So there should be no negative sign. For simplicity, maybe what I can do is that all of this negative sign I can take out. So all of this negative sign. So I can redefine things. So there will be one extra negative sign outside. You can write h minus bf and then sigma dot I del or rather grad, let me write grad, and minus e a, and then psi of r equal to e of psi of r, right? So that's what we can write actually, because p we can write minus I grad k, right? Sorry, grad, this is in real space, grad r, this is valid, right? Because k we can write minus I h bar uh, del x, let's say. So if we do this, if we start from this, there will just be a negative sign which is troubling me, because this is correct actually. So this I need to renormalize. So this is called non-dimensionalization of the Hamiltonian. So if you start progressing from this equation, let's say equation 1, you can actually easily arrive at uh, expression something like this: h cap psi y, sorry, psi, and then minus E by VF psi, okay, where H cap is given by 0 EBY minus KX minus del Y EBY minus Kx plus del Y 0. So there is just a negative sign, okay. That negative sign is picked up in the right hand side, and also we have
Okay.
also uh, transferred the VF Fermi velocity in the right hand side, just energy by VF. Okay, now if you define this xi is a dimensionless quantity, because LB is simply root over h bar by EB, which has a dimension of length, and y is also has also dimension of length. So this is dimensionless quantity. Now we want to write this Hamiltonian operator in terms of xi, let's say. So for that, what we can do is that del y is simply we can do del xi del y and then del xi, right? You can write this by chain rule. So del xi del y is simply 1 by LB, and then this is del xi. So this Hamiltonian can be written as 0 and so EB y and minus, let me multiply by LB, just a second. Somewhere I missed h bar or not. So this definition actually should be k is equivalent to minus I by sorry, there should not be any h bar in when I do k I del x, let's say, right, for k. And when I do this p is h bar k, there should be an h bar. Okay, so if I have this h bar here extra, I have h bar extra here also. So I have EBY minus h bar kx minus h bar del ky, or del y, and EBY, and okay, so minus h bar kx my plus h bar del y and I want to write in terms of xi, let's say. So I need to have y by LB and LB times kx. So I'll take h bar common. So h bar 0 EB y by h bar minus kx minus h bar del y EB y by h bar minus kx plus del y 0, and so this will be h bar 0 y by LB square minus kx minus h bar del y y by LB square minus kx plus, sorry, there will be not be any h bar here also, del y 0, and I need y by LB. So if I take another LB common, h by LB 0, y by LB minus kx LB minus LB del y, and y by LB minus kx LB plus LB del y 0. So what I got, h bar by LB, and this term is simply xi, so 0 xi minus, so I had del y equal to 1 by LB del xi del xi del y is okay, 1 by LB del xi. Right. So 1 by LB del xi and xi plus, sorry, what I'm doing. So
I think
this
yeah, there should not be LB. Yeah,
LB,
just yeah.
and then del y means this term. So 1 by LB del xi, right? So
So
LB
you're
by
just del by del xi.
right. So that's I wanted to do.
Yeah. Yes.
So h bar is simply given by h bar by LB 0 xi minus del xi plus del xi 0, and xi is dimensionless. Okay. So there are, if you have not taken minus sign, that was also fine, but then problem was in h bar. Okay, so this is my Hamiltonian. Okay, now again we want to write the energy eigenequation, which will be this h bar and then simply the phi y, let's say phi y, just because e to the, so in the both side there are e to the power ikxx, which cancels out kind of, and this will be uh, I want to send minus e by vf and then sorry, so this side will be h bar and lb, right? And phi y. Okay, so let me call it phi sorry, h cap tilde. Okay, because so h tilde cap is simply, or rather h cap is simply h tilde cap into h bar by lb. Okay, I just sent this down, and let's call it some e tilde. Okay, minus phi y. So E tilde is some energy and then some length scale and so on. Properties of magnetic field is also there. Properties of the material is also there. Okay. So now I want to define some operator. So this is H tilde cap phi of y. Okay. Now I want to define some operator such that so this is, let's say, my one of the operator plus del xi and O dagger cap is simply 1 by root 2 xi minus del xi. Okay, so, such that my h tilde becomes so h tilde simply becomes 0 oh my god, so this is bad notation, so let's call it simply a. So a cap, so this was plus at the, okay, a dagger. So this is my new h tilde. Okay, but the only thing that will be there is that there will be 1 by root 2 here, or the other way around. Let me see. I have introduced 1 by root 2 in the xi and del xi, so there will be root 2 here actually, right? And if you do the commutation relation, you'll find that this a and a dagger operators follow this commutation relation. It is just simply one, just like other operators. So if you remember, we had the harmonic potential, or rather simple harmonic motion in the quantum mechanics, where we had a dagger equal to 1, right? Where a dagger was the raising operator,
Yes,
which
sir.
creates
Yes, sir.
an particle at that point or at that momentum or real space. It depends on where you define this operator. And a was the lowering operator. Now this Hamiltonian again looks like kind of similar kind of harmonic oscillating operator, which follows the same. Sorry, this was not 0. This was 1. So which follows the same relation. So we can think of that. Again, essentially here also we'll have some Hermite polynomial type of wave function that will satisfy the this h tilde, and that can solve the Hamiltonian, right? And here this phi y will actually be phi xi, right? Because everything is in terms of xi, where xi of course depends on the y, and this phi xi will simply be some, let's say, phi a of xi and phi b of xi. Okay, because we had a Hamiltonian in the basis of a and b sublattice. Okay, this is not to be confused with the a operator, but a sublattice and b sublattice. So this is written in a sublattice and this is written, let's say, in b sublattice. So that's how there is consistency. So if it is written in a sublattice, b sublattice, and this is also written in A sublattice, B sublattice, so you will get consistent A and B, right? So these are the components of the wave function in the A sublattice and B sublattices. Okay. Now for eigenvalues, now for solving the eigenvalue, we want to actually take h bar square, okay, of phi xi, and which will be e tilde square phi xi. I'm not solving, I'm just following the steps, and this phi xi form will be this psi n minus 1 of xi, some normalization constant, let's say n phi n xi. Okay, let me write it small n and psi n is the uh, SHM wave function, basically Harmonic polynomials, which have the property of all those property which are valid for the uh, simple harmonic oscillator in the quantum mechanics first phase. Okay, so this type of wave function you need to take, and then you will solve the Hamiltonian and you will get the energy as h bar omega c root over n, where omega c will also be proportional to root over b, and there will be some other factor, electrons and so on, electronic charge and so on. Okay, so this is the Landau level energy for the graphene. Now what is interesting about this or of this solution is that this is for the, let's say, so this type of wave function is valid for when n not equal to 0. Okay, now when n equal to 0, now when the case where energy equal to 0, or rather n equal to 0, let's say for n equal to 0 you will have energy also 0. So I have done some mistake, so this will be n minus 1. Okay, okay, so for n equal to 0, if you take phi xi, you end up with psi minus 1 xi and n some normalization constant psi 0 of xi, right? So this is the equation for n, let's say, and this is for n equal to 0. So you end up with psi minus 1, but there was no state like minus 1 in the simple harmonic oscillator, right? You had n equal to 0, 1, 2 and so on. So this, by definition, you have to take phi of xi, let's say 0, some normalization constant psi of 0 xi. So this is the new wave function you need to take for sorry. Okay, so this is the new wave function that you need to take for the zeroth Landau level, or for the n equal to 0 state. Okay, so what you see from this expression, so if you need to, so if you take this kind of phi of xi, what will really happen is that h tilde of phi of xi will be energy equal to, so energy is already 0 for our zeroth state, then you will have 0 a dagger 0, and then I'm just explicitly writing there, so 0 or rather, okay, so there is another way to motivate in a more fundamental way. So here we have, I have already said that this needs to be taken. So let's not take this thing and see what really happens. So I have similar same thing, right? Phi A of xi, phi B of xi. Sorry for this, but so this was energy equal to 0, and phi A of xi, phi B of xi, and what will happen? So this is simply 0 a dagger 0, and then phi a, and then phi b. I'm not writing the argument of xi, so this was simply 0 because energy is 0 in our case. So this equation, this the above equation gives rise to uh, a phi b equal to 0 and a dagger phi a equal to 0, right? This is the two equation. Now from first equation, what we can get is that a dagger is the lowering operator. Okay, and a sorry, a is the lowering operator and a dagger is the raising operator. Yeah, it's correct. Right. Huh. Now we are searching for the ground state, which is the lowest energy, right? Lowest energy, which is zero energy, right? So for now, for ground state, what do we need? So if we lower, if we apply lowering operator to some phi b, let's say. Now phi b can be harmonic oscillators nth, any nth wave function, let's say. N goes to 0, 1, 2, 3, 4. So what is the possibility? What are the possibilities for the ground state? So the possibility is that phi b of xi will be psi n equal to 0 of psi. Okay, and this psi is the simple harmonic motions or the harmonic potentials wave function, and phi a will simply be completely 0. So that's how you can have this ground state, because uh, if phi a is some finite states, let's say, I mean some finite n equal to 0, 2, 3, or 1, 2, 3, then you can raise this operator, right? So you will not have ground state. So if we have something phi xi equal to I am taking, let's say, phi a equal to 1 state. Okay, so psi 1, let's say, of SHM, and phi b equal to, let's say, n equal to 0. So this is not the ground state. The ground state is the lowest possible energy state. So the only possibility that is left for us is that it becomes completely 0 and it remains as ground state. So that the raising operator, because notice that this is the, on the phi a we are applying raising operator. So if we have already one, then it will raise to psi 2. Similarly, if we have a dagger, it will have I'm messing up, but let's see. A dagger, let's say I have psi 1, okay, and this is for phi a, scenario for phi a. So if we apply a dagger on the psi 1, it will simply be some constant or some value into psi 2. Similarly, a dagger, if we apply psi 0, again some value psi 1. So in, and so on. So if it is giving psi 1 to psi 2, then for psi 2, psi 3, all of those are again more and more higher. So the only, even if you take psi 0 at place of phi a in this wave function or the spinor, then you get some excited state, but we need the lowest ground state, which is the zero energy. So that's why this is 0, which is phi a is 0, which is the case here. And for phi b, what will happen is that we take the lowest possible state, so that there is some state and it cannot be lowered further. Okay, so this is the condition a cap phi b, right? So in the phi b, in place of phi b, we take the lowest possible state, so it is kind of already ground state, it cannot go further down. So psi 0 is the lowest ground state for the harmonic potential in quantum mechanics, right? So if you apply this should be 0, which is true uh, for the lowest ground state, because uh, the condition, so let me write it again: 0 a cap a dagger 0. Now I am writing in terms of, let's say, harmonic potential psi n psi n, psi n a psi n b. Okay, a sublet is b sublet is, and in this, on the right hand side, both are 0. You remember that. So I need any, in all possible, I need to have 0. Now imagine the situation. This, okay, so I need to use different color. This acts on this one, this acts on this one in the matrix multiplication. So even if you take psi in A to be psi 0 A sublattice and zeroth state of the SHM, then you have some higher state already, right? But in this area, on the right hand side, you have only 0. And here, A dagger psi NB, if you take psi 0 A dagger, it will be 0, because psi 0 is the lowest state, it cannot go down. So I hope this was clear. It was a bit mathematical. And what this translates into is that this is 0, this is psi 0. So this means that in the lowest Landau level for the graphene, you have A sublattice completely empty and B sublattice, it is the ground state. So this is, let's say, for the K value. And if you do similar calculation for the K prime value, you will get something different, exactly opposite. So it will be occupied for the A sublattice, and it will be 0 for the B sublattice. So I hope this was clear. This was a bit mathematical, but I'll come with some more physically motivated reason. But let me know if
Yeah,
you have any questions.
yeah, thanks a lot. I think I need to go through the calculation to convince me that I understood. But thanks for giving the idea overall, and I mean explaining all these things.
Right. So
Do
it
you
was
have some
kind of
resources in mind,
okay.
or
So
uh, or some books I can consult just to make sure
no,
if I get
actually,
all the steps right?
so books, you can,
Ah,
of course, consult the Girvin's book, Quantum Hall Effect by Girvin, but
okay.
that
There
will
one.
be, I think, heavy book.
Uh-huh.
But
Okay. Okay. I'll see to it. Thank you.
so let me send these two things. One is that how this Dirac cone comes as linear in momentum, and some
Yes.
more easy to understandable resource. I have all three of your
Uh,
email IDs, so I'll send it.
Thanks a lot.
So it
Thanks a
may
lot.
take
Thanks a lot.
at least 2 days, but yeah.
No problem, sir. Thanks a lot. Thanks a lot.
Okay.
Okay.
So let's stop here. Thank you for joining on the Sunday.
Yeah. Thanks for your explanations. Nice weekend to you.